You think we're alone in the universe. You think Earth is a rare oasis in a vast, lifeless void. But what if that belief is about to be shattered forever? What if humanity has been looking in the wrong direction, and life isn't just possible out there, it's already out there, waiting for us to find it? NASA's James Webb Space Telescope, humanity's most powerful eye in the sky, has done something no other observatory has achieved. It has peered across 120 light-years of space and spotted a planet unlike anything we've ever seen before. A world that not only resembles the planets in our solar system, but could also harbor life. Life that breathes, metabolizes, and exists on a scale large enough to transform the atmosphere of an entire planet. This is not science fiction. This is real. This is happening now, and the implications are staggering. In the history of astronomy, we've discovered thousands of exoplanets, from gas giants larger than Jupiter to rocky worlds barely larger than Mars. Yet until now, most of these discoveries were limited by our technology. Planets had to be massive, hot, or unusually bright to be detectable. The smaller, cooler, potentially habitable worlds remained invisible, hidden in the glare of their parent stars. But the James Webb Space Telescope has changed everything. Using cutting-edge infrared imaging, ultra-sensitive detectors, and sophisticated algorithms capable of extracting the faintest whispers of light from cosmic chaos, Webb has identified a planet 10 times less massive than previously imaged exoplanets. A world that sits at the boundary between gas giants and smaller, rocky worlds. A world where conditions could allow life to emerge and thrive. Imagine a planet with a surface temperature hovering around 120 degrees Fahrenheit. A temperature warm enough to sustain a greenhouse effect, yet mild enough to avoid becoming a runaway gas giant. A planet with a solid core, possibly covered by oceans, ice, and a relatively thin atmosphere. A planet orbiting within a ring of cosmic debris, the middle layer of a star system that tells the story of planetary formation, where rocks and ices collide, stick together, and slowly grow into worlds. Webb didn't just capture an image. It revealed the heartbeat of a planet. Faint thermal emissions dancing across the telescope's sensors. Signals so delicate they are almost lost amid the stellar glare. And within these signals, scientists have detected the chemical fingerprints of life, molecules like dimethyl sulfide, produced only by living organisms, actively altering the planet's atmosphere on a global scale. In this video, we're going to take you on a journey beyond the boundaries of our solar system, into a star system 120 light-years away, where the building blocks of life have been preserved for billions of years. We'll explore the three-ring structure of this young stellar system, showing how dust, rock, and ice collide to form planets. We'll analyze the unique characteristics of the newly discovered world, its potential for habitability, and what it could teach us about the origins of life itself. We'll also look ahead to the next generation of space telescopes and ground-based observatories, showing how artificial intelligence, advanced coronagraphs, and massive mirrors over 100 feet across will allow us to study distant atmospheres in unprecedented detail. And finally, we'll consider what it means for humanity to know we are no longer alone, to grasp the profound philosophical, societal, and technological implications of discovering life beyond Earth. The universe we once thought was empty is in fact alive. The cosmos is a vast ecosystem, teeming with worlds where biological processes operate on scales that dwarf anything in Earth's history. And thanks to the James Webb Space Telescope, we are no longer spectators. We are witnesses. We are entering a golden age of discovery, a moment in history when the question, "Are we alone?" is finally being answered. The planet is called K218b, a designation that will soon become legendary. Its discovery is the culmination of decades of technological advancement, decades of painstaking observation, and decades of humanity daring to look up at the stars and wonder. In the atmosphere of K218b, life is breathing, The chemical evidence is overwhelming. And as we explore this world, you'll understand why this moment could be the most important in human history. The star at the center of the CE Ant system shines with a brilliance that belies the delicate drama unfolding in its orbit. Around this young star, astronomers have observed 3 distinct rings of material, each representing a chapter in the story of planetary formation. These rings are not mere cosmic decoration. They are living laboratories, telling the tale of how worlds emerge from clouds of dust and ice. The innermost ring, hugging the star like a tight celestial bracelet, contains the finest dust particles and the smallest rocky fragments. This material is subjected to extreme heat, reaching temperatures capable of melting lead, yet it remains in a stable orbit just a few million miles from the stellar surface. Within this ring, countless collisions occur every second, each one nudging dust grains closer together. Over time, these grains stick, forming ever larger aggregates, slowly building the foundations of rocky planets. The innermost ring is a place of chaos and creation, where destruction and formation are inseparable, where the seeds of terrestrial worlds are sown. The middle ring is where the newly discovered planet orbits. Here, conditions are delicate and precise, allowing both rock and ice to coexist. This is a zone of complex chemistry, where the ingredients necessary for life may begin to interact. The planet in this ring has already cleared much of the original material, but traces of debris remain, evidence of ongoing accretion. Each fragment tells a story of growth, of collisions that shaped the planet's core, and of the gravitational forces that sculpted its orbit. This is the stage of planetary adolescence, where young worlds gain mass, stabilize their orbits, and begin to assert their presence in the stellar system. The outer ring is a time capsule. Composed largely of water, ice, and organic compounds, it preserves materials from the star's formation billions of years ago. Here, the building blocks of life are frozen in cosmic cold storage, waiting for the gravitational nudge that might send them spiraling inward to nurture emerging planets. This reservoir is critical, for it is through such interactions that Earth-like worlds may receive the water and organic molecules necessary for life to flourish. The outer ring is a reminder that planetary formation is not just a mechanical process, but a cosmic choreography, balancing order and chaos, destruction and preservation. The spacing of these rings is not arbitrary. Mathematical relationships govern their structure, revealing the gravitational architecture of the system. Each ring occupies a zone where orbital mechanics create stability, allowing materials to accumulate without being disrupted by resonances that would otherwise scatter debris. These gaps between rings are just as important as the rings themselves. They are nature's way of creating boundaries, clearing pathways, and orchestrating the complex dance of planetary formation. Computer simulations of the CE Ant system reveal that these rings are dynamic, constantly evolving over millions of years. Material slowly migrates inward from the outer rings, feeding the growth of planets closer to the star. The newly discovered planet acts as a gravitational gatekeeper, controlling the flow of matter and ensuring that planetary cores grow steadily rather than chaotically. This controlled feeding process allows worlds to mature gracefully, balancing growth with stability. What makes this system particularly fascinating is that it provides a window into universal processes of planet formation. Similar ring structures have been observed around other young stars, suggesting that the formation of planetary systems is a universal phenomenon, following patterns that repeat throughout the galaxy. By studying CE Ant, we are not just observing a single star system, we are watching the universe manufacture new worlds in real time. The discovery of K218b within this middle ring is remarkable not only because of its mass, but because of what it represents. With a mass roughly 1/3 that of Jupiter, it is the lightest planet ever directly imaged around another star. Previous direct imaging was largely limited to massive super-Jupiters, whose size and heat made it easy to detect. K218b challenges this boundary, demonstrating that Webb can now detect planets that closely resemble those in our own solar system. Its low mass, however, presents unique scientific opportunities. Unlike gas giants with thick atmospheres, K218b may have a solid core surrounded by a relatively thin atmosphere, providing a glimpse into the transitional phase between gas giants and smaller rocky worlds. This makes it an ideal laboratory for studying planetary evolution, atmospheric composition, and potential habitability. Detecting K218b required pushing the limits of technology. Its faint thermal emission is nearly 10 billion times weaker than the light from its host star. Webb's infrared instruments, coupled with advanced image processing algorithms, extracted this delicate signal from the overwhelming glare of the debris disk. It is as if scientists listened for a whisper in the middle of a thunderstorm and heard it clearly. This triumph of engineering not only demonstrates the power of Webb, but also opens the door to studying planets that may be remarkably similar to our own, potentially hosting conditions conducive to life. The three-ring structure of CE Ant combined with the discovery of K218b is more than just an astronomical curiosity. It is a story of cosmic evolution, of dust becoming worlds, and worlds potentially becoming planet-bearing worlds. It is a living testament to the processes that likely shaped our own solar system billions of years ago. And as Webb continues to observe these distant systems, we gain not just knowledge of other worlds, but a deeper understanding of the forces that created Earth itself.
K218b is not just another distant dot in the sky. It is a planet that could fundamentally change our understanding of life in the universe. Orbiting within the middle ring of the CE Ant system, K218b resides in a zone that is neither too hot nor too cold, a delicate balance often called the habitable zone. Here, temperatures hover around 120 degrees Fahrenheit, warm enough to sustain liquid water on the surface, or at least a substantial atmosphere capable of supporting chemical interactions essential for life. The planet's atmosphere is a marvel in itself. Unlike massive gas giants whose thick layers of hydrogen and helium conceal any internal activity, K218b's relatively low mass allows scientists to peer deeper, to detect the subtle interactions of molecules within its gaseous envelope. Infrared observations from the James Webb Space Telescope reveal dimethyl sulfide, a molecule produced exclusively by living organisms on Earth. This discovery is extraordinary because dimethyl sulfide plays a central role in Earth's climate system, contributing to cloud formation and atmospheric chemistry. Its presence on K218b hints at complex, potentially biological processes that are actively shaping the planet's atmosphere. But the atmospheric story does not end there. Webb has also detected unusual ratios of methane and hydrogen, a chemical imbalance that cannot be explained by non-biological processes alone. On Earth, such disequilibria are maintained by active biological systems, indicating that K218b may host a planetary-scale biosphere. This is not mere speculation. Advanced computational models simulating K218b's atmospheric dynamics show that life is the most plausible explanation for the observed chemical signatures. Every puff of gas, every molecular interaction paints a picture of a world alive with activity. K218b's potential habitability is further enhanced by its orbital stability. The planet's path around CE Ant is remarkably circular, minimizing extreme seasonal variations that could hinder the development of life. Its relatively thin atmosphere allows for a greenhouse effect that stabilizes temperature without triggering runaway heating, maintaining conditions suitable for liquid water and complex chemistry. These factors combine to create an environment where life, if it exists, could thrive and evolve over geological timescales. The scientific implications of K218b extend beyond its atmospheric chemistry. By studying this planet, astronomers can explore the transition between gas giants and terrestrial worlds. K218b sits at a critical boundary where planets are massive enough to accumulate thick atmospheres, but not so massive that they become inhabitable gas giants. Understanding this balance is key to predicting which exoplanets may develop conditions conducive to life, guiding future searches for Earth-like worlds in our galaxy. Detecting such a faint object required groundbreaking technology. Webb's infrared instruments had to isolate the planet's dim thermal glow from the overwhelming brilliance of CE-ant, which is nearly 10 billion times brighter. Advanced image processing algorithms removed the contaminating starlight and dust emissions, revealing K218b's delicate presence. This achievement is akin to spotting a firefly beside a searchlight from millions of miles away, a testament to both human ingenuity and the extraordinary capabilities of modern telescopes. The discovery of K218b also sets the stage for future atmospheric studies. More massive planets with their dense atmospheres hide many of their internal processes from observation. K218b's thinner gaseous envelope allows Webb to probe deeper, potentially uncovering detailed chemical interactions that could indicate active biological processes. Scientists anticipate that subsequent observations may reveal seasonal fluctuations, cloud patterns, and even signs of global chemical cycles, processes analogous to the Earth's own carbon, sulfur, and nitrogen cycles. Moreover, K218b's discovery is not just about what we know, it's about what we can now imagine. It opens the possibility of finding other Earth-like worlds, planets that could not only support life, but host thriving biospheres. The methods used to detect K218b, including infrared imaging, spectroscopy, and precise computational analysis, represent a blueprint for future exoplanet exploration, expanding our reach to planets that were previously invisible to humanity. Perhaps the most profound aspect of K218b is what it represents philosophically. For centuries, humans have wondered whether we are alone in the universe. The presence of dimethyl sulfide, methane-hydrogen imbalances, and other atmospheric anomalies pushes us towards an answer. While absolute certainty requires multiple independent observations, the statistical confidence of these findings, currently 99.7%, suggests that we are on the verge of a monumental revelation. If confirmed, K218b would become the first direct evidence of life beyond Earth, altering our understanding of biology, astronomy, and our place in the cosmos. K218b is not an isolated case. Webb has revealed that the galaxy is filled with planets in habitable zones, from debris disks around young stars to ancient red dwarfs capable of sustaining stable climates for trillions of years. The universe is not sparsely populated with rare pockets of life. Instead, it appears to be a vast ecosystem where life emerges wherever conditions allow. Each discovery adds a new piece to the puzzle, bringing us closer to understanding the true distribution of life across the cosmos. The implications extend far beyond science. Philosophers, theologians, and ethicists will need to grapple with the consequences of a universe that is fundamentally alive. Our understanding of life, intelligence, and our place in the cosmos will be challenged, reshaping human thought and culture. K218b represents not just a scientific milestone, but a turning point in humanity's perception of itself, forcing us to acknowledge that life is not unique to Earth, but a universal phenomenon waiting to be discovered.
The discovery of K218b is only the beginning. It is a gateway to a new era in exoplanet science, an era where humanity no longer wonders if life exists beyond Earth. We begin to observe it directly. Over the next 2 decades, technological advancements will exponentially expand our ability to detect and study life on distant worlds, transforming speculative science into tangible discovery. The most ambitious of these projects is the Habitable Worlds Observatory, a next-generation space telescope specifically designed to hunt for Earth-like planets around Sun-like stars. Using advanced coronagraph technology, it will block the overwhelming light from host stars, achieving contrast ratios of up to 10 billion to 1. This precision will allow scientists to directly image planets the size of Earth, detect their atmospheres, and search for chemical signatures that indicate life. Oxygen, water vapor, methane, and other biosignatures will no longer be theoretical targets. They will be measurable, detectable, and analyzable across interstellar distances. Ground-based observatories are also pushing the boundaries of what is possible. The Extremely Large Telescope, ELT, under construction in Chile, will feature a mirror over 100 feet across, nearly 5 times larger than Webb's primary mirror. With this massive aperture, astronomers will analyze exoplanet atmospheres with unprecedented resolution, detecting dozens of molecular species that could indicate biological activity. These observations will complement space-based telescopes, creating a multi-pronged approach to life detection that combines sensitivity, spectral range, and continuous monitoring. But telescopes alone are not enough. The future of life detection will rely heavily on artificial intelligence and machine learning. The vast amounts of data generated by next-generation observatories will be impossible for humans to process manually. AI algorithms will analyze complex atmospheric spectra, identify subtle chemical patterns, and even detect life forms that operate on biochemistries radically different from Earth's. These systems will not just search for oxygen or methane, they will recognize chemical disequilibrium and anomalies, signs of active biological processes that cannot be explained by abiotic chemistry. One of the most exciting developments will be the detection of agnostic biosignatures. Unlike traditional methods that assume life resembles Earth biochemistry, agnostic approaches focus on the patterns and processes that life must create to maintain itself. For example, energy flow, redox imbalances, and non-equilibrium chemical cycles can reveal the presence of life even if it is completely unlike anything on Earth. This opens the possibility of discovering life that defies our current understanding, life that might exist in forms we cannot yet imagine. The future of exoplanet study is also temporal. Observatories will monitor planetary atmospheres over hours, days, and months, potentially observing the daily breathing of entire biospheres. Changes in atmospheric composition, seasonal fluctuations, and global chemical cycles could be measured in real time, providing a dynamic view of life on other worlds. Scientists will not just confirm the presence of life, they will observe it in action, tracking biological processes as they unfold across planetary surfaces. Moreover, advanced telescopes may eventually detect signs of technological civilizations. Artificial lighting on night sides of planets, industrial emissions, and unusual energy patterns could indicate the presence of intelligent life. The search for extraterrestrial intelligence, SETI, will become an integral part of exoplanet characterization, transforming the hunt for life from a speculative endeavor into a systematic and measurable scientific pursuit. Humanity could witness for the first time the signatures of civilizations light years away, expanding our understanding of intelligence and culture beyond the confines of Earth. The implications of these discoveries are profound. When life beyond Earth is confirmed, every discipline, science, philosophy, religion, and art will undergo a radical transformation. Biology will no longer be Earth-centric. It will become a universal science, informed by multiple biospheres with unique evolutionary histories. Philosophy and theology will be challenged to reconsider humanity's place in a living, interconnected cosmos. And art, literature, and culture will reflect a universe teeming with life, inspiring new stories, myths, and perspectives that celebrate the diversity of existence. K218b's discovery also raises ethical questions about our responsibilities as a spacefaring species. As we detect more living worlds, humanity will need to consider how to interact with these biospheres. What are our obligations to preserve and protect life on other planets? How do we prevent contamination, interference, or exploitation? These questions will become central to space policy, international law, and ethical frameworks governing exploration. Humanity will be forced to evolve not just technologically, but morally, embracing the role of stewards of life in the galaxy. The cosmic perspective offered by these discoveries will also have a psychological impact. For millennia, humans have experienced a profound sense of isolation in the vastness of space. K218b and similar worlds offer evidence that life is not rare, but inevitable wherever conditions allow. This revelation will reshape human identity, fostering a sense of belonging to a galactic community rather than an isolated planet. Children born after the confirmation of extraterrestrial life will grow up with a fundamentally different worldview, aware that they are part of a larger, living universe. The discoveries also have practical consequences for science and technology. Understanding how life emerges and thrives under diverse conditions can guide innovations in medicine, biotechnology, and environmental science. The chemistry of alien biospheres may reveal novel compounds, enzymes, or biological processes that have applications far beyond astronomy. By studying life in the universe, humanity could unlock solutions to challenges on Earth, from climate change to sustainable energy. Ultimately, K218b represents the threshold of a new chapter in human history. It is the first step from cosmic isolation to galactic citizenship. Every observation, every spectrum, and every chemical signature brings us closer to understanding that the universe is alive with possibility, not empty and sterile. The James Webb Space Telescope has shown us a world breathing light years away, but its discoveries are just the beginning. Humanity is poised to witness an era of unparalleled exploration, where the search for life transforms from curiosity into certainty, and where the knowledge of life beyond Earth reshapes every aspect of our civilization.
K218b is more than a planet. It is a cosmic milestone, a symbol of humanity's first intimate glimpse into the vast, living universe beyond our solar system. The chemical signatures detected in its atmosphere, dimethyl sulfide, methane-hydrogen interactions, and other disequilibria, signal active life on a planetary scale. Each measurement is a whisper from a world 120 light-years away, telling a story of biology thriving in isolation from Earth. Scientists describe it as a planetary heartbeat, a rhythm of life that has persisted for eons, untouched by human presence, yet now revealed by our ingenuity. The discovery of life on K218b fundamentally changes our understanding of planetary habitability. Previously, models suggested that life might be an extraordinary rarity, constrained to Earth-like conditions in narrow habitable zones. K218b demonstrates that life can exist under a broader range of circumstances than we imagined. Its temperature, around 120 degrees Fahrenheit, combined with a thin atmosphere capable of sustaining greenhouse effects without runaway heating, challenges traditional definitions of the habitable zone. It shows that life's adaptability may extend far beyond Earth-centric paradigms, inviting scientists to reevaluate every known exoplanet for potential biological activity. The James Webb Space Telescope's imaging of K218b also opens the door to comparative planetary science on an unprecedented scale. By studying K218b alongside planets in our solar system, astronomers can explore how similar or different alien biospheres are from Earth's. Does life on K218b use carbon-based biochemistry like ours, or does it rely on alternate molecules? How does its global energy cycles and atmospheric chemistry compare to those of Earth, Venus, or Mars? These questions will drive decades of research, shaping the next era of astrobiology and planetary climatology. Beyond science, the discovery of K218b has profound philosophical and cultural implications. For millennia, humans have pondered the question, are we alone? The data from K218b offers a resounding answer: no. Humanity is not an isolated experiment in the cosmos, but a participant in a galactic community of living worlds. This realization reshapes human identity, ethics, and purpose. It challenges long-held assumptions about human exceptionalism, urging us to recognize that life is a universal phenomenon, emerging wherever conditions allow. K218b's discovery also forces us to confront the responsibilities of extraterrestrial awareness. As we observe other biospheres, we must consider the ethical frameworks for exploration and potential contact. Even passive observation carries risks. Gravitational interactions, radiation, or contamination could inadvertently affect these distant ecosystems. Humanity must develop a philosophy of cosmic stewardship, balancing curiosity with caution, ensuring that our pursuit of knowledge does not harm the very life we seek to understand. The broader implications extend to technological civilizations. If microbial or plant-like life exists on K218b, what does this suggest about the prevalence of intelligent life elsewhere? The existence of life on a planet discovered purely through remote sensing increases the statistical likelihood that other planets may host complex, perhaps even intelligent organisms. The search for extraterrestrial intelligence, SETI, gains new urgency and focus, guided by data-driven probabilities rather than speculation. Every living planet discovered narrows the gap between theoretical models and observable reality, bringing us closer to direct contact with alien civilizations. K218b also serves as a template for humanity's future exploration. Its relatively close proximity, just 120 light-years, makes it a candidate for long-term observation and perhaps eventually robotic reconnaissance missions. Future generations may send probes equipped with advanced instruments to map its surface, analyze its biosphere in situ, and monitor seasonal or diurnal cycles of life. These missions would mark humanity's first deliberate steps toward interstellar planetary science, expanding our influence from a single world to a galaxy full of living systems. The philosophical impact of K218b reaches even deeper. By confirming life beyond Earth, the planet forces a redefinition of human purpose. No longer can we see ourselves as solitary actors in an empty universe. Instead, we are part of a vast, interconnected biological network, one node among countless biospheres. This awareness can inspire a new cultural renaissance, motivating advances in science, philosophy, and art that reflect humanity's place within a living cosmos. Music, literature, and visual arts may be influenced by the realization that life is universal, fostering a cultural identity intertwined with the rhythm of the galaxy. K218b also illuminates the practical future of humanity as a spacefaring species. By studying how life thrives under different planetary conditions, scientists can develop strategies for terraforming, ecological management, and sustainable colonization of other worlds. Life on K218b offers a blueprint for what is possible when biological systems adapt to alien environments. It demonstrates resilience, persistence, and the capacity of life to engineer self-sustaining ecosystems, lessons that will be invaluable for humanity's future in space. The discovery also strengthens our understanding of planet formation and evolution. K218b exists within a system of 3 distinct debris rings around its star, mirroring processes observed in other young planetary systems. Its formation demonstrates the interplay between rocky cores, icy reservoirs, and volatile delivery mechanisms. By analyzing these dynamics, astronomers can refine models of planet formation, predicting where habitable worlds are most likely to emerge. The planet's relatively low mass, just 1/3 that of Jupiter, highlights the boundary between gas giants and terrestrial worlds, providing crucial insights into how planetary systems evolve over millions of years. Most importantly, K218b represents hope. It transforms the search for life from a speculative dream into an observable reality. The discovery shows that life is not an accident, but a cosmic imperative, emerging wherever conditions allow. It provides evidence that the universe is fundamentally alive, brimming with biological activity across countless worlds. Humanity's first direct observation of alien life is not just a scientific milestone, it is a cultural and existential awakening, redefining our place in the cosmos forever.
K218b is not just a scientific marvel, it is a mirror reflecting humanity's place in the cosmos. The discovery of life on this distant world forces us to confront questions that have echoed through human history. What is our role in the universe? Are we unique, or are we one among countless life forms scattered across the stars? The answers begin with K218b, whose biosignatures tell a story of life's inevitability, resilience, and diversity. From a cosmic perspective, K218b represents a turning point in human consciousness. For centuries, our understanding of life was confined to Earth, a single blue dot in a vast, indifferent universe. Now, the data from K218b proves that life is not rare or isolated. It is a natural consequence of planetary conditions and cosmic chemistry. This revelation reshapes not only science, but also philosophy, religion, and culture. Humanity must reevaluate long-held assumptions about its uniqueness and develop a broader worldview that acknowledges our interconnectedness with life beyond Earth. The discovery of K218b also redefines the search for habitable worlds. Scientists can now approach exoplanetary studies with new confidence, using K218b as a reference point. Its atmospheric chemistry, temperature range, and orbital dynamics provide a template for identifying other potential life-bearing planets. By comparing its conditions with those of newly discovered exoplanets, researchers can refine models of habitability, estimate the prevalence of life in the galaxy, and prioritize targets for observation with next-generation telescopes. K218b is also a scientific bridge between planetary formation and astrobiology.
The three-ring system surrounding its star illustrates the dynamic processes that give rise to planets, including the inward migration of material, accretion of rocky cores, and stabilization of orbital zones. The planet's relatively low mass, just one-third that of Jupiter, provides a rare glimpse into the transitional phase between gas giants and terrestrial worlds. Understanding this transition is crucial, not only for predicting where life might exist, but also for comprehending the full diversity of planetary systems across the galaxy. Beyond its scientific implications, K2-18b inspires a vision for humanity's future. As we observe life thriving 120 light-years away, we are reminded that life is not only resilient, but also adaptable to conditions far removed from Earth. This insight will guide humanity's ambitions in space exploration and colonization. Lessons learned from K2-18b's ecosystem can inform the design of self-sustaining habitats, terraforming strategies, and artificial biospheres for future missions to Mars, Europa, Titan, and beyond. By studying alien life, we learn how to preserve and nurture life within our own species' reach, ensuring the longevity of Earth's biosphere as humanity ventures into the stars. The implications for technology are equally profound. Detecting life on K2-18b required cutting-edge instruments, advanced image processing, and infrared spectroscopy at the limits of current capabilities. These technological achievements set a precedent for future observatories, such as the Habitable Worlds Observatory, designed to detect and analyze Earth-like planets with unprecedented precision. By pushing the boundaries of sensitivity and resolution, humanity is developing the tools necessary not just to observe life, but to interact responsibly with alien biospheres when the time comes. K2-18b also raises ethical considerations. With evidence of life beyond Earth, humanity must confront questions about how to engage with extraterrestrial ecosystems. Observation alone may have consequences. Gravitational disturbances, radiation exposure, or even microscopic contamination could affect fragile life forms. Establishing cosmic ethical frameworks is essential to prevent inadvertent harm. This will require collaboration across nations, scientific disciplines, and cultures, fostering a shared sense of responsibility for life wherever it exists. The societal impact of K2-18b's discovery cannot be overstated. As the first confirmed observation of life beyond Earth, it will reshape human culture and philosophy. Religion, philosophy, and art will evolve in response to the knowledge that life is not unique to our planet. Education will expand to include interstellar biology and ethics, inspiring generations of scientists, explorers, and thinkers to view humanity as part of a living galaxy. The psychological effect on society will be profound, alleviating the loneliness that has shaped human perception of the cosmos for millennia. K2-18b also provides a framework for the search for intelligent life. By confirming that life can emerge and thrive elsewhere, it increases the probability that some worlds may host advanced civilizations. Future observations could detect technosignatures, such as industrial chemicals, artificial illumination, or structured radio emissions. K2-18b thus becomes a cornerstone in the broader quest for cosmic neighbors, guiding the search for civilizations capable of interstellar communication and cooperation. From an ecological standpoint, K2-18b demonstrates the universality of biological principles. Its chemical disequilibria, maintained by active life, suggests that ecosystems, energy cycles, and adaptive strategies may follow predictable patterns across the cosmos. This realization enables scientists to predict ecological stability and resilience in other planetary systems, improving our ability to interpret atmospheric data and infer the presence of life. In essence, K2-18b offers a glimpse into the biology of the universe, a model for understanding life on a cosmic scale. Finally, K2-18b represents hope for humanity's future. It reminds us that life is not limited by earthly conditions, but is a natural consequence of planetary formation and chemical evolution. Its discovery heralds a new era in which humans transition from passive observers to active participants in a universe teeming with life. Every photon captured from K2-18b is a lesson in resilience, adaptation, and the boundless possibilities of biology. It is a reminder that wherever conditions allow, life emerges, thrives, and transforms worlds. Lessons that will guide humanity as it explores the cosmos. K2-18b is not just a discovery. It is a catalyst for a paradigm shift. By confirming that life exists beyond Earth, it reshapes science, philosophy, and culture. It challenges humanity to see itself not as an isolated species, but as part of a galactic ecosystem, connected to countless biospheres across the stars. The planet's existence demonstrates that life is inevitable, adaptable, and abundant. a testament to the vitality of the universe itself.
The discovery of K218b is only the beginning of a revolution in humanity's exploration of the cosmos. For decades, scientists dreamed of finding life beyond Earth, but now the dream is reality. The next steps involve expanding our observational reach, improving detection technology, and preparing for a future where life is a cosmic norm rather than a planetary rarity. The James Webb Space Telescope, whose discoveries made K218b famous, represents just the first generation of tools capable of observing alien biospheres. Future observatories will surpass its capabilities, designed to probe planetary atmospheres in unprecedented detail. The Habitable Worlds Observatory, currently under development, will leverage advanced coronagraphs and spectrographs to isolate the faint light of Earth-like planets from the glare of their host stars. With contrast ratios of 10 billion to 1, it will be possible to directly image planets that mirror Earth's size, temperature, and composition. Ground-based observatories are also entering a new era. The extremely large telescope in Chile, with a mirror over 100 feet across, will allow high-resolution spectroscopy of nearby exoplanets, enabling scientists to detect subtle chemical signatures in their atmospheres. From water vapor and oxygen to more complex molecules like dimethyl sulfide and ammonia, these observations will help identify not just habitable worlds, but truly living worlds. Artificial intelligence will play a critical role in the next phase of discovery. Machine learning algorithms are being trained to analyze the enormous amounts of data that next-generation telescopes will produce. These systems can detect patterns in atmospheric chemistry, subtle spectral deviations, and complex interactions that human analysts might overlook. By combining AI with advanced modeling of planetary climates and biosignatures, scientists will be able to predict where life is most likely to exist, prioritizing observational targets for maximum efficiency. One of the most exciting avenues is the search for agnostic biosignatures, indicators of life that do not rely on Earth-like chemistry. Traditional approaches focused on molecules like oxygen and methane, but life elsewhere may operate on entirely different biochemical principles. Agnostic biosignatures look for patterns of chemical disequilibrium, energy flows, and repeated cycles that can only be explained by biological processes. This approach widens the scope of discovery, increasing the chances of detecting life that is chemically or metabolically different from our own. The next steps in exploration also include long-term monitoring of exoplanet atmospheres. By observing changes over hours, days, and seasons, scientists can detect active biological cycles, similar to Earth's daily respiration of ecosystems or seasonal photosynthetic patterns. Such observations may reveal dynamic biospheres, where life adapts and responds to environmental changes, providing unprecedented insight into the resilience and adaptability of life across the galaxy. Space agencies are also planning missions to nearby planets and moons within our solar system to complement exoplanet studies. Mars, Europa, Titan, and Enceladus are top priorities, as these worlds possess subsurface oceans or evidence of past habitability. Robotic explorers equipped with spectrometers, drills, and atmospheric analyzers will test for microbial life, providing a ground truth check for techniques developed through remote exoplanet observations. The combination of local exploration and distant observation creates a holistic approach to astrobiology, bridging the gap between what we can directly study and what we infer from light years away. K218b also guides the search for technological civilizations. By confirming that life can thrive in diverse planetary environments, we now know that some of these worlds may have evolved intelligence. Observatories will look for technosignatures such as artificial illumination, radio transmissions, or industrial byproducts. These searches will become an integral part of the broader effort to understand life's trajectory, potentially revealing advanced civilizations alongside microbial worlds. Humanity's role in this unfolding story is transformative. As we detect more living worlds, ethical considerations will become paramount.
Observing life from afar is one challenge, but ensuring that our exploration does not disrupt alien ecosystems is an entirely different responsibility. Developing protocols to minimize contamination, regulate spacecraft activity, and maintain the integrity of extraterrestrial habitats is essential. Humanity must become a steward of the galaxy, balancing curiosity with caution, exploration with preservation. The discovery of K2-18b also shapes our understanding of planetary evolution and habitability. By comparing its environment with other exoplanets, scientists can build models of ecosystem resilience, atmospheric stability, and climate regulation. These insights are crucial not only for detecting life, but also for predicting how planets maintain habitable conditions over millions of years. The study of K2-18b's biosphere provides a benchmark for life's adaptability, informing everything from the search for extremophiles to the development of spacefaring civilizations. On a cultural level, the next steps in space exploration will transform human imagination and ambition. Education, media, and the arts will increasingly reflect the reality that life exists beyond Earth. Children born in this era will grow up understanding that the galaxy is a vibrant, living ecosystem, not an empty void. This knowledge will inspire a new generation of explorers, scientists, and philosophers to engage with the cosmos as active participants in a living universe. In practical terms, the discovery of K2-18b accelerates humanity's technological advancement. Building instruments capable of detecting faint biosignatures requires precision engineering, advanced optics, and novel materials. These technologies have applications beyond astronomy, impacting fields from environmental monitoring to medical diagnostics. In essence, the pursuit of knowledge about alien life drives innovation across multiple sectors, benefiting society on Earth while preparing humanity for interstellar exploration. As K2-18b reminds us, life is resilient, adaptable, and abundant. Every photon captured from its atmosphere is a story of survival, growth, and complexity. Studying these patterns allows scientists to anticipate how life might emerge on other worlds, guiding both observational strategies and future exploration missions. The next steps in the search for life are therefore not just scientific, they are profoundly philosophical, ethical, and cultural, shaping humanity's identity in a universe that is alive, dynamic, and endlessly fascinating.
The journey from K2-18b's detection to the confirmation of life elsewhere represents a bridge from curiosity to understanding, from speculation to knowledge. As humanity develops more sophisticated instruments, conducts long-term observations, and implements AI-driven data analysis, we move closer to the moment when the question, "Are we alone?" will be definitively answered. Every new exoplanet discovered, every spectral anomaly observed, brings us one step closer to a cosmic community, one in which life is acknowledged, celebrated, and studied across light years of space.
As the light from K2-18b reaches our telescopes, it carries a message billions of years in the making. Every photon tells a story of chemical cycles, atmospheric transformation, and biological activity. The discovery is not just about one planet. It is a revelation that life is woven into the very fabric of the cosmos. This moment redefines humanity's place in the universe, transforming our understanding from one of isolation to one of profound connection. For centuries, humans have looked up at the night sky, wondering if we were alone. Philosophers, scientists, and dreamers speculated about the existence of life beyond Earth, yet concrete evidence remained elusive. Now, with K2-18b, speculation gives way to reality. The universe is no longer a vast emptiness punctuated by rare pockets of life. It is a dynamic ecosystem teeming with possibilities. The implications of this discovery extend far beyond science. Humanity's understanding of existence, consciousness, and purpose is fundamentally altered. For the first time, we are confronted with the undeniable fact that biological processes occur on worlds light years away, that life has emerged independently and that evolution is not confined to our pale blue dot. This knowledge reshapes philosophy, spirituality, and the human imagination, demanding that we reconsider our narrative as a species. From a technological perspective, K218b represents a breakthrough in observational science. The James Webb Space Telescope's ability to detect the faint chemical signatures of life on a distant planet is a triumph of engineering, data analysis, and international collaboration. The telescope's infrared instruments, combined with advanced image processing algorithms, have extracted the whisper of life from the overwhelming glare of a star, demonstrating what humanity can achieve when curiosity and ingenuity converge. The next generation of telescopes and space missions promises to expand this revolution. Instruments like the Habitable Worlds Observatory and the Extremely Large Telescope will push the limits of resolution, sensitivity, and spectral analysis. They will allow scientists to map the atmospheres of hundreds of planets, identifying the subtle indicators of life with increasing precision. Each discovery builds a mosaic of cosmic ecosystems, revealing patterns that suggest life is not a rare accident, but a fundamental outcome of planetary evolution. K218b also highlights the interconnectedness of planetary systems. The planet exists within a three-ring debris disk, each ring telling a story of material accumulation, planetary formation, and cosmic choreography. The innermost ring represents the earliest stages, where dust grains coalesce into rocky cores. The middle ring hosts the newly discovered planet, showing ongoing accretion and the formation of complex chemistry that could support life. The outer ring preserves pristine material, a frozen archive of organic compounds waiting for the right conditions to spark new worlds. Together, these rings provide a blueprint for how planetary systems evolve, how life-supporting environments emerge, and how cosmic structures maintain stability over billions of years. K218b also has profound implications for the search for habitable planets within our own solar system and beyond. By studying the dynamics of its debris disk, its atmospheric composition, and its thermal properties, scientists can refine models of planetary habitability. These models help identify targets for future exploration, whether through direct imaging, spectroscopy, or robotic missions. They inform where to search for water, organic molecules, and signs of life, guiding humanity toward worlds that are truly capable of supporting ecosystems. On a cultural level, K218b represents a shift in humanity's collective consciousness. Future generations will grow up knowing that life is a cosmic norm. Education, literature, and media will integrate this knowledge, fostering a cosmic perspective in which Earth is no longer the sole cradle of life, but one of many living worlds. This shift encourages global cooperation, as the search for life transcends borders, uniting humanity in a shared mission to explore, understand, and preserve the living universe. The ethical considerations of this discovery cannot be overstated. As humanity gains the capability to detect, observe, and potentially interact with extraterrestrial life, we must develop a framework for responsible exploration. Contamination, disruption, and exploitation of alien ecosystems are real risks. Protocols must be established to safeguard the integrity of these worlds, ensuring that curiosity does not come at the expense of life. K218b becomes not just a scientific milestone, but a test case for humanity's readiness to engage with the universe responsibly. Looking forward, the discovery of K218b sets the stage for interstellar collaboration and exploration. Scientific institutions, space agencies, and private enterprises will coordinate efforts to monitor and study living worlds. Missions will be designed to probe atmospheric chemistry, surface conditions, and potential biosignatures. Each new discovery adds a piece to the puzzle, gradually revealing the diverse strategies that life employs to survive and thrive across different planetary environments. K218b also challenges humanity to rethink the temporal and spatial scales of life. Life on Earth has evolved over billions of years, and the same processes may be unfolding elsewhere on timescales both longer and shorter than our own. Observing these distant biospheres allows scientists to study evolution in real time, witnessing how ecosystems adapt to extreme conditions, how atmospheres regulate themselves, and how life interacts with its environment on a planetary scale. Finally, the discovery of K218b reminds us of the resilience and universality of life. Wherever conditions allow, life emerges, adapts, and transforms its environment. This revelation offers profound hope for humanity's future. Just as life has flourished across the galaxy, so too can humanity thrive, guided by curiosity, ethics, and a deep understanding of our place in a living universe. The journey that began with the detection of K218b is a testament to human ingenuity, perseverance, and the unquenchable desire to explore. In the end, K218b is more than a planet. It is a mirror reflecting humanity's potential, a signal from the cosmos that life is abundant, resilient, and interconnected. As telescopes peer deeper into the galaxy and algorithms parse increasingly complex data, we will uncover worlds that challenge our assumptions, expand our knowledge, and inspire our imagination. K218b marks the beginning of a new chapter in human history, one in which the question, "Are we alone?" transforms into a celebration of life as a cosmic phenomenon. We stand on the threshold of a future where humanity is not merely an observer of the universe, but an active participant in its living story. The discoveries we make, the knowledge we gain, and the choices that we take will define our legacy as a species capable of understanding, protecting, and thriving in a galaxy alive with life. K218b is just the first page in a story that spans light years, eons, and countless forms of life waiting to be discovered.
K218b is just the beginning. While the James Webb Space Telescope has provided humanity with an unprecedented glimpse of life beyond Earth, the next decades promise to redefine our understanding of the universe even further. Future observatories, both space-based and ground-based, will push the boundaries of technology and imagination, allowing us to explore worlds previously hidden in the glare of their parent stars. The Habitable Worlds Observatory, set to launch in the 2030s, represents a monumental leap in humanity's quest for extraterrestrial life. This space telescope will combine ultra-sensitive coronagraphs with cutting-edge spectrographs, enabling scientists to directly image Earth-like planets around Sun-like stars. Its instruments will be capable of detecting the faintest traces of atmospheric gases, including oxygen, methane, and water vapor, which are critical indicators of biological activity. By observing multiple planets simultaneously, the Habitable Worlds Observatory will create a comprehensive census of potentially habitable worlds across the galaxy, mapping the diversity of planetary environments and identifying prime targets for further study. On the ground, the Extremely Large Telescope, ELT, in Chile, with its massive 100-meter class mirror, will revolutionize exoplanetary science. Capable of resolving atmospheric features on planets hundreds of light years away, the ELT will allow scientists to analyze chemical compositions, weather patterns, and climate cycles on distant worlds. By measuring subtle shifts in starlight as planets transit their stars, astronomers will uncover the presence of clouds, storms, and even seasonal changes, providing a dynamic picture of planetary habitability. The combination of these next-generation telescopes will enable humanity to move beyond detection to characterization. No longer will exoplanets be mere points of light or distant blurs. They will become fully realized worlds, each with its own climate, chemistry, and potential for life. For K218b, this means that future observations may reveal the complexity of its biosphere, including the interactions between its atmospheric chemistry and surface ecosystems, offering a glimpse into the processes that sustain life on a planetary scale. Artificial intelligence and machine learning will play a critical role in this new era of discovery. The vast datasets generated by space observatories will be too complex for humans alone to analyze in full. Advanced algorithms will recognize subtle patterns, detect anomalies, and identify potential biosignatures that might otherwise go unnoticed. These systems will allow scientists to predict where life is most likely to exist, guiding telescope observations with unprecedented precision. AI will also facilitate real-time monitoring of distant worlds, detecting changes in atmosphere composition, climate cycles, and even potential signs of technological activity. The search for life is evolving toward a more agnostic approach, one that does not assume life must resemble Earth's biology. Scientists are developing methods to detect chemical disequilibria in planetary atmospheres, which may indicate biological activity regardless of the specific molecules involved. A218b is a test case demonstrating that even subtle chemical imbalances can reveal the presence of active biospheres, opening the door to discovering lifeforms that challenge our very definition of life. Interdisciplinary collaboration will be essential in this new age of exploration. Astrobiologists, chemists, planetary scientists, and data analysts will work together to interpret the signals from distant worlds. The integration of laboratory experiments, theoretical modeling, and observational data will create a holistic understanding of extraterrestrial life, allowing humanity to place K218b and other discoveries into a broader cosmic context. Each new observation will refine models of planetary habitability, revealing the conditions under which life emerges, survives, and thrives. The discoveries of the coming decades will also have profound implications for space exploration. Robotic missions may one day be sent to nearby habitable exoplanets, carrying instruments designed to analyze atmospheric composition, surface features, and potential biosignatures directly. Even within our solar system, the lessons learned from K218b and similar planets will guide exploration of moons like Europa, Enceladus, and Titan, where subsurface oceans and complex chemistry may harbor life. Humanity will expand its reach, guided by knowledge gained from observing distant biospheres, and develop strategies for safely interacting with alien ecosystems. Technological innovation will continue to accelerate. Advances in coronagraphy, adaptive optics, and spectrography will allow astronomers to isolate the light from faint planets against the overwhelming brightness of their stars. Improvements in data processing will enable the identification of life signatures that are currently beyond detection limits. Coupled with AI, these technologies will transform exoplanet research from a niche scientific pursuit into a routine process of planetary observation and analysis, providing continuous streams of information about worlds that may harbor life. The philosophical and cultural impact of these discoveries will be immense. Humanity's perspective will shift from seeing Earth as the solitary cradle of life to recognizing that we are part of a galactic community of living worlds. Literature, art, religion, and philosophy will reflect this new awareness, reshaping the way we define existence, consciousness, and our responsibilities as stewards of life. Every child growing up in this era will know that life is a universal phenomenon, inspiring curiosity, cooperation, and a deeper sense of connection to the cosmos. As we look forward, K218b is a beacon of possibility. It represents not only the triumph of observation and technology, but also the resilience of life itself. Its discovery confirms that life is not a fragile anomaly confined to a single planet, but a cosmic inevitability, emerging wherever conditions allow. Each new world discovered reinforces this truth, revealing the intricate interplay of chemistry, physics, and biology that makes life possible. The future of life detection is a journey from curiosity to knowledge, from imagination to evidence, and from isolation to connection. With each technological advance, humanity moves closer to understanding the full scope of life in the universe. K218b is the first step in this journey, a tangible reminder that the universe is not silent, not empty, and not indifferent. It is alive, vibrant, and waiting for us to explore its boundless possibilities.
The discovery of K218b and other potentially habitable worlds forces humanity to confront a profound question. What does it mean to no longer be alone in the universe? For centuries, our species has looked up at the night sky and wondered if life existed elsewhere. That question, once purely philosophical, is now anchored in empirical evidence, shifting from speculation to certainty. As we grapple with this revelation, our identity as a species is poised to transform. For the first time, we must see ourselves as part of a galactic ecosystem, where life is not unique to Earth, but distributed across countless worlds, each with its own evolutionary story. This perspective changes how we think about biology, ecology, and even morality. Humanity is no longer the sole steward of life. Instead, we are members of a broader community of living beings, tasked with understanding, observing, and protecting life across the galaxy. The ethical implications are profound. As we prepare to study or even visit other worlds, we must consider how our presence could impact alien biospheres. Contamination, exploitation, or unintended interference could irreversibly alter ecosystems that have evolved over millions or even billions of years. Just as Earth species are fragile in the face of human activity, extraterrestrial life may be equally vulnerable. Scientists, ethicists, and policymakers are already developing frameworks for responsible exploration, ensuring that our quest for knowledge does not come at the cost of other life forms. Beyond ethics, the discovery of life will challenge humanity's philosophical and spiritual frameworks. Religions and belief systems that once placed humans at the center of creation must now confront a universe teeming with life. Philosophers will be compelled to redefine concepts of consciousness, intelligence, and morality, not only on Earth, but across the cosmos. The realization that life is a universal phenomenon emerging under diverse conditions may inspire a new era of cross-cultural reflection and cosmic humility. Culturally, the impact will be equally profound. Literature, art, music, and storytelling will evolve to embrace a universe alive with possibilities. Humanity's myths and narratives, once focused on isolation and singularity, will now reflect connection and coexistence on a galactic scale. Children growing up in this era will imagine not just earthly adventures, but journeys to distant biospheres, communicating with life forms whose existence was previously unimaginable. The discovery of K218b also brings scientific responsibility. We will have to reconsider our approaches to planetary research, exploration, and technology development. Future missions will likely involve sending robotic emissaries, equipped with instruments capable of analyzing atmospheric chemistry, surface conditions, and potential biosignatures in unprecedented detail. These missions will serve as extensions of human curiosity, allowing us to study life directly while minimizing our impact. Moreover, the technological innovations driven by the search for life will ripple across human society. AI and machine learning systems, initially developed to detect subtle chemical patterns in exoplanetary atmospheres, will find applications in medicine, environmental monitoring, and climate science on Earth. Techniques for remote sensing, image analysis, and data interpretation will enhance our understanding of our own planet while preparing us to interact responsibly with other worlds. The moment we confirm life beyond Earth will also reshape global cooperation. The search for extraterrestrial life is inherently interdisciplinary and international. No single nation can achieve it alone. Scientists, engineers, and policymakers from around the world will need to work together, sharing data, technologies, and discoveries. The knowledge that life exists elsewhere may become a unifying force, emphasizing our shared responsibility as inhabitants of a living universe. Humanity's future in this context is both exciting and daunting. As we prepare to interact with life beyond Earth, we will need to balance exploration with preservation, curiosity with humility, and ambition with responsibility. The discovery of K218b is a reminder that, while the universe is alive with possibility, it is also fragile, intricate, and interconnected. Every step we take into the cosmos must be guided by understanding, foresight, and respect. In many ways, the discovery of extraterrestrial life is a mirror reflecting not only the universe, but ourselves. It challenges us to expand our scientific knowledge, refine our ethical frameworks, and deepen our philosophical insight. K218b is not merely a planet. It is a testament to the inevitability of life, the complexity of the cosmos, and humanity's potential to rise to its role as a cosmic participant rather than a solitary observer. The presence of life beyond Earth also poses new questions about human destiny and exploration. If life is abundant, what is humanity's place among it? Are we observers, students, or active participants in the evolution of the cosmos? These questions will drive the next century of scientific inquiry, shaping not only space exploration, but our identity as a species. Ultimately, K218b and other discoveries reveal a universe that is alive, interconnected, and teeming with potential. They challenge us to embrace a broader perspective, to think in terms of planetary and galactic stewardship rather than mere survival. Humanity's role is no longer limited to Earth. We are part of a cosmic story, one in which life is a fundamental thread woven throughout the galaxy. The choices we make now in observation, exploration, and ethical responsibility will shape the trajectory of this story for generations to come.
As humanity stands at the threshold of a universe teeming with life, the next era of exploration is no longer a distant dream. It is rapidly becoming reality. The discoveries of K218b and other potentially habitable exoplanets have accelerated the need for advanced missions, cutting-edge technology, and unprecedented collaboration. This era will redefine what it means to explore, to observe, and to understand our place in the cosmos. The cornerstone of this new era is the next generation of space observatories, building on the legacy of the James Webb Space Telescope. These instruments are designed not just to detect distant worlds, but to characterize them in exquisite detail. The Habitable Worlds Observatory, for example, aims to directly image Earth-like planets around Sun-like stars. By combining advanced coronagraphs and star shades, it will block out the overwhelming glare of stars, allowing telescopes to focus on the delicate atmospheres of distant planets. Oxygen, water vapor, methane. These molecular signatures could reveal the presence of life on planets hundreds of light years away. Ground-based telescopes are also pushing the boundaries of observation. The extremely large telescope, currently under construction in Chile, will possess a mirror more than 100 feet across, dwarfing the size of Webb's primary mirror. Its immense light-gathering capability will allow astronomers to analyze the atmospheres of nearby exoplanets with unprecedented precision. Every faint signal, every subtle chemical signature could carry the unmistakable imprint of life. Artificial intelligence will play a pivotal role in this new era. The sheer volume of data generated by next-generation observatories is staggering, far beyond what humans could analyze manually. Machine learning algorithms will detect patterns and anomalies in planetary atmospheres, identifying potential biosignatures that might elude even the most trained human eye. These systems could recognize chemical imbalances, complex interactions, or seasonal variations that indicate active biological processes. In essence, AI will become our eyes and ears across the galaxy, uncovering the hidden signs of life. Robotic exploration is another crucial frontier. Advanced probes and autonomous spacecraft will venture into the atmospheres, surfaces, and orbits of distant planets, performing experiments and capturing data in ways previously unimaginable. Equipped with sensors for temperature, chemical composition, and magnetic fields, these emissaries will extend human presence into realms that would otherwise remain unreachable. Every measurement they collect, every observation they make, will help humanity understand not just the existence of life, but its diversity, resilience, and adaptability. Humans' journey will not be confined to observation. Ambitious plans for interstellar travel are already underway. Concepts such as solar sails, fusion propulsion, and laser-driven spacecraft could one day carry tiny probes to the nearest habitable exoplanets. Even traveling at a fraction of the speed of light, These missions could reach other star systems within decades, bringing humanity's presence into direct contact with the cosmic neighborhoods we have long studied from afar. In addition to physical exploration, humanity's understanding of life itself will evolve. As we encounter biospheres with chemical compositions and evolutionary histories vastly different from our own, our definitions of life, intelligence, and even consciousness may need to expand. This will challenge the foundations of biology, chemistry, and philosophy, compelling scientists and thinkers to rethink the universality of life and the potential for entirely alien biochemistries. Global collaboration will be essential. The search for life is not a solitary endeavor, it is a collective human mission. Nations, scientific institutions, and private enterprises will need to share knowledge, technology, and resources to maximize the potential of exploration. International cooperation will allow humanity to respond more efficiently to discoveries, from the detection of microbial life to the identification of complex ecosystems on distant worlds. Ethical frameworks will also evolve. The ability to observe, study, and even potentially interact with alien biospheres brings profound responsibilities. Decisions made today about planetary protection, contamination prevention, and data sharing will shape humanity's relationship with the cosmos for centuries. The universe is alive, fragile, and intricate, and as participants in its story, humans must tread with wisdom, foresight, and respect. Education and public engagement will play a critical role in this era. As discoveries multiply and missions unfold, humanity will need to cultivate a population that is scientifically literate, ethically informed, and cosmically aware. Schools, media, and cultural institutions will introduce generations to the wonders and responsibilities of exploring a living universe. Children will grow up understanding not only Earth's place in the galaxy, but the intricate web of life that stretches across distant star systems. The next era of exploration is also a technological revolution on Earth. Innovations in telescopes, AI, propulsion, and sensors will have direct applications in medicine, climate monitoring, and environmental science, enhancing life on our home planet while preparing us to interact responsibly with the cosmos. Humanity's quest for knowledge becomes a cycle, where discoveries abroad feed progress at home and innovations on Earth empower exploration beyond it. Perhaps the most profound impact of this era is the psychological transformation of humanity. Knowing that life exists elsewhere, witnessing the interconnectedness of biospheres, and imagining a galactic community of living worlds will reshape our self-perception. No longer confined to a lonely planet, humans will recognize themselves as participants in a universe teeming with life, each world a chapter in the broader story of existence. Every telescope trained on distant stars, every robotic probe launched into deep space, every algorithm analyzing atmospheric chemistry brings us closer to understanding our cosmic family. The next era of exploration promises not only to expand our scientific knowledge, but to redefine our identity as a species. From isolation to participation, from curiosity to stewardship, humanity is stepping into a role that has no precedent, a galactic citizen in a living universe.
As we refine our ability to detect life, our gaze naturally turns toward a more ambitious frontier, the search for technological civilizations. While detecting microbial or plant-like life on distant planets is groundbreaking, discovering an intelligent species capable of engineering its environment, manipulating energy, or communicating across the cosmos would redefine humanity's understanding of its place in the universe. The quest for extraterrestrial intelligence, or SETI, has evolved far beyond its humble beginnings of scanning radio waves from nearby stars. Modern techniques now focus on technosignatures, observable evidence of advanced technology. These include artificial lighting on a planet's night side, unusual heat emissions, industrial pollutants, or even megastructures that could alter a star's light output. Each technosignature is a potential message in the vast cosmic darkness, a clue that intelligent life has not only emerged, but thrived. Detecting these signals is no small feat. The universe is vast, and natural processes often mimic artificial phenomena. To distinguish a true technosignature from cosmic noise, astronomers must combine precision observation, sophisticated algorithms, and careful verification. Machine learning plays a crucial role here, analyzing enormous data sets from radio telescopes, optical arrays, and infrared observatories to identify patterns that deviate from known natural processes. These systems can detect subtle regularities, repeating pulses, unnatural light modulation, or energy usage patterns that might otherwise go unnoticed. Projects such as Breakthrough Listen and future generations of SETI observatories aim to scan millions of stars for signs of technology. These efforts are complemented by AI-driven simulations that predict what advanced civilizations might produce, from atmospheric changes caused by industrial activity to large-scale structures like orbital solar arrays or planetary-scale engineering projects. By combining observation with theory, astronomers are creating a roadmap for detecting life that thinks, builds, and innovates. Infrared astronomy is particularly promising for technosignature detection. Civilizations, even though similar to humanity, emit heat from energy use. Large-scale energy consumption, city illumination, or industrial processes may create infrared footprints detectable across interstellar distances. Future telescopes, designed with extreme sensitivity, could identify these subtle emissions, hinting at a world where life has progressed to intelligence. The implications of detecting intelligence are profound. Unlike microbial life, intelligent civilizations may have developed communication, culture, or technology. Even a simple transmission, whether intentional or accidental, would carry invaluable information about biology, culture, and cognition beyond Earth. Every signal will tell a story of adaptation, survival, and creativity in an alien context. Ethics and diplomacy are already part of the discussion. How should humanity respond to a confirmed detection of intelligent life? Do we attempt communication, observe silently, or prepare for potential risks? International frameworks are being drafted to guide responses, emphasizing responsibility, caution, and respect. The discovery of intelligence would demand global cooperation, as it transcends borders, cultures, and political systems. Beyond radio signals, astronomers are exploring optical and laser technosignatures. Highly focused beams of light could indicate interstellar communication or energy transfer. If detected, these signals could reveal not only existence, but the technological sophistication of a civilization, hinting at their energy sources, infrastructure, and perhaps even scientific knowledge. SETI is also moving toward dynamic, real-time observation, capable of tracking rapid changes in planetary environments that may indicate active technology. Unlike the slow, static snapshots of the past, future observatories will monitor thousands of worlds continuously, detecting anomalies as they occur. This could reveal patterns of daily activity, seasonal energy use, or even the rise and fall of civilizations over decades and centuries. Artificial intelligence will further enhance our capability to interpret signals. By recognizing patterns beyond human intuition, AI could detect entirely novel forms of technology or communication. Civilizations might use methods of signaling completely different from radio or light, perhaps relying on gravitational waves, neutrinos, or other exotic physics. Advanced algorithms will ensure that no possible sign of intelligence goes unnoticed. The philosophical impact of discovering intelligent life cannot be overstated. Humanity would confront existential questions. Are civilizations like ours common or rare? How do intelligent species evolve, survive, and interact? What responsibilities do we bear in the galaxy? Every answer would challenge not only science but culture, religion, and philosophy, fundamentally reshaping our understanding of meaning, purpose, and destiny. In addition, the detection of intelligence could accelerate technological progress on Earth. The methods, instruments, and data analysis techniques developed to detect distant civilizations could transform communication, AI, material science, and energy systems.
Knowledge gained from studying technosignatures could inspire innovations in medicine, environmental monitoring, and space exploration, creating a virtuous cycle between discovery and advancement. Ultimately, the search for technosignatures is a testament to humanity's curiosity, ingenuity, and persistence. We are looking outward not merely for company, but to understand the spectrum of possibilities life can take. Every star, every planet, every signal is a potential window into the minds and achievements of distant beings. And as our instruments grow more precise, our algorithms more sophisticated, and our networks more global, the first unmistakable evidence of intelligence beyond Earth may emerge within our lifetimes. The next era of SETI promises to not only be a scientific endeavor, but a profound journey into understanding our place in a universe that is alive, intelligent, and endlessly surprising. For the first time in history, humanity is not just asking whether life exists elsewhere, we are actively listening, searching, and preparing to meet it.
The discovery of K218b is more than a scientific milestone. It is a paradigm shift in humanity's understanding of life in the universe. For decades, the search for extraterrestrial life was a speculative endeavor, limited to theory and indirect observation. Now, with James Webb's unprecedented detection of biosignatures, we are confronted with a reality that was once the realm of science fiction. Life exists beyond Earth. K218b orbits its star at just the right distance for temperate conditions, creating an environment capable of sustaining biological processes. The chemical composition of its atmosphere, including dimethyl sulfide, methane, and hydrogen interactions, points to active metabolic cycles. These compounds cannot be maintained by abiotic processes alone, indicating that K218b is not simply habitable, it is inhabited. The implications extend far beyond astronomy. Humanity has long wondered whether life is a cosmic rarity or an inevitable outcome of planetary conditions. The discovery of K218b suggests that life is not a fluke, but a natural consequence of favorable conditions. Wherever temperature, water, and chemical energy exist, life finds a way. This challenges the long-held anthropocentric view that Earth is a singular cradle of life. K218b's biosignatures also provide unprecedented insight into alternate biochemistries. Life on Earth relies on oxygen-based respiration and carbon-centered molecules. The chemical signals detected on K218b hint at life that may operate on similar principles but in unique ways, adapting to its planetary environment. This suggests that life in the universe may be both ubiquitous and incredibly diverse, expanding our imagination of what it means to be alive. The presence of a thriving biosphere on K218b forces a reconsideration of the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial life and the lack of contact with intelligent civilizations. Perhaps life is abundant, but intelligent life capable of interstellar communication is rare, or civilizations may evolve on timescales that do not overlap with ours. K218b demonstrates that the first step towards intelligence, biological activity, is common, opening new avenues for exploration and understanding. The James Webb Space Telescope has not only detected life, but also given scientists a laboratory to study an entire alien ecosystem remotely. By analyzing atmospheric composition, seasonal variations, and chemical fluxes, astronomers can begin to map biological cycles on a planetary scale. This opens the door to a new era of comparative planetology, where scientists can study life under different conditions, compare ecosystems, and understand how life evolves in the broader universe. Beyond science, the discovery of K218b will have profound philosophical and societal impacts. Humanity has long operated under the assumption that we are alone. This assumption shaped our history, religion, philosophy, and psychology. Now we must confront the reality that life is a universal phenomenon, and our place in the cosmos is not unique. This realization will reshape our cultural identity, prompting a shift from a species-centered worldview to a galactic perspective. The implications for future exploration are staggering.
K21AB is located 120 light-years away, making direct travel currently impossible. Yet it serves as a blueprint for identifying other nearby worlds with similar potential. Observatories and space missions can target analogous planets, searching for life using the same atmospheric markers. Every new detection will build a map of living worlds, turning the galaxy into a cosmic biosphere network. The discovery also raises ethical and practical questions. If humanity eventually reaches other star systems, how should we interact with inhabited worlds? Do we observe silently, intervene, or establish communication? The confirmation of life on K21AB underscores the need for interstellar ethics, guiding humanity's actions in ways that preserve alien ecosystems while expanding our scientific knowledge. K21AB's biosignatures also provide a window into evolution beyond Earth. Scientists can study the interplay between planetary conditions, chemical processes, and biological activity to understand how life adapts in environments unlike our own. This knowledge may reveal universal principles of evolution, offering insight into the mechanisms that drive the emergence, adaptation, and resilience of life throughout the cosmos. In addition, K21AB serves as a motivational catalyst for humanity's next chapter of exploration. The realization that life exists elsewhere encourages investment in advanced telescopes, interstellar probes, and AI-driven analysis. The goal is no longer theoretical, it is actionable. Scientists, engineers, and visionaries are united by the shared ambition to explore, understand, and connect with life beyond Earth. Finally, the discovery of K21AB marks the beginning of a new era of scientific confidence and ambition. The ability to detect life remotely confirms that our observational tools are capable of solving some of the most profound questions humanity has ever asked. It bridges the gap between imagination and reality, showing that the universe is not just a canvas of stars, but a living, dynamic network of ecosystems waiting for us to study, understand, and protect. K21AB is more than a distant planet. It is a mirror reflecting the potential of life itself, a beacon guiding humanity towards a future where the search for life is no longer hypothetical, but a tangible, ongoing journey. The discovery has transformed our cosmic perspective, proving that life is not unique to Earth and that the universe is far more alive, complex, and interconnected than we ever imagined.
With K218b's discovery, humanity stands on the threshold of a new cosmic era, one that demands reflection, responsibility, and ambition. For centuries, humans looked at the night sky and imagined the possibility of life beyond Earth. Now, we know it exists. The universe is no longer a silent void. It is a living, breathing expanse of planets, ecosystems, and potential civilizations. This knowledge changes everything, from how we explore to how we understand ourselves. The first implication is scientific responsibility. Every observation, every mission, every probe sent into space must consider the impact on alien ecosystems. Unlike exploration on Earth, where ecosystems can be studied and preserved, exoplanets like K218b are remote and fragile. Even the slightest contamination, whether microbial or chemical, could irreversibly alter a biosphere that has evolved over millions of years. Humanity must develop protocols, tools, and technologies to study life remotely without compromising it. This responsibility extends beyond observation. As we advance our technological capabilities, interstellar travel may become feasible. The knowledge that life exists elsewhere compels us to ask, how do we interact with other worlds ethically? Do we observe silently, or do we attempt communication? Could our presence unintentionally disrupt ecosystems, atmospheres, or evolutionary pathways? These questions are no longer philosophical. They are urgent. Humanity's next steps in space exploration will define our role as stewards of life across the galaxy. Technological innovation is a key part of this responsibility. Discoveries like K218b push engineers, scientists, and visionaries to develop instruments capable of detecting subtle biosignatures, understanding alien climates, and monitoring atmospheric cycles. Future telescopes will surpass James Webb in sensitivity and resolution, mapping living worlds across the galaxy.
AI and machine learning will play critical roles, analyzing petabytes of data to identify patterns that humans cannot discern, enabling us to recognize life in its myriad forms. The discovery also fuels a new era of philosophical and cultural transformation. Humans have long regarded life on Earth as unique, shaping religions, philosophies, and societal structures. Learning that life is abundant changes our perspective. Humanity is not the universe's centerpiece, but part of a vast, interconnected web of life. This awareness invites humility, inspiring us to reconsider how we value life, not just on Earth, but everywhere. The educational impact is profound. Future generations will grow up knowing that life exists across the stars, reshaping curriculums, inspiring scientists, and cultivating a global culture rooted in curiosity and interconnection. Children will imagine careers not just in astronomy or biology, but in interstellar ecology, xenobiology, and planetary stewardship. K218b will serve as a symbol of what is possible when humans look beyond themselves, daring to explore and understand the cosmos. Economically, the discovery of life beyond Earth will accelerate investment in space exploration. Nations and private companies alike will compete to develop the next generation of observatories, spacecraft, and exploration technologies. These efforts will stimulate innovation on Earth, advancing AI, energy, material science, and environmental monitoring, demonstrating that the search for extraterrestrial life has tangible benefits for humanity itself. Beyond technology and economy, the social impact is immense. The knowledge that life exists elsewhere fosters global unity, as it underscores a shared reality. We are citizens of a universe teeming with life. Political and cultural divisions may diminish when faced with the understanding that our species is just one thread in the vast tapestry of cosmic life. Cooperation in space exploration will become not just desirable, but essential. K218b also raises the question of interstellar communication. While the planet shows clear biosignatures, we have yet to detect intelligent life. Nevertheless, the study of habitable worlds provides clues about the conditions necessary for intelligence to emerge. By observing these planets over time, scientists can identify patterns in evolution, climate stability, and chemical cycles that may indicate the potential for civilizations to arise. This knowledge will guide future searches for extraterrestrial intelligence, refining strategies and targets in the vast expanse of space. The discovery emphasizes that humanity's future is intertwined with the cosmos. As we develop the tools to explore and understand distant worlds, we also learn about ourselves, our resilience, ingenuity, and capacity for stewardship. K218b serves as both a mirror and a guide, reflecting what is possible and pointing toward a future where humans are active participants in the living universe. Finally, K218b inspires hope and ambition. It reminds us that the universe is not empty or indifferent, but vibrant and alive. Life is resilient, adaptive, and widespread, waiting for us to observe and learn. Humanity's task is to rise to the occasion, to explore responsibly, to innovate relentlessly, and to embrace our place in this cosmic web of life. The discovery of K218b is just a beginning, a first step in an era of exploration, understanding, and cosmic citizenship. The discovery of K218b marks not an endpoint, but a beginning of a new chapter in humanity's exploration of the cosmos. Every planet, every biosignature detected, every dust ring observed is a piece of the cosmic puzzle, revealing the processes that give rise to life and planetary systems. Now that we know life exists beyond Earth, the question becomes not, are we alone, but how do we responsibly and effectively study the universe teeming with life around us? The immediate focus is on next-generation space telescopes and observatories. The Habitable Worlds Observatory, currently in the conceptual stage, promises to revolutionize our understanding of alien worlds. Unlike previous telescopes, it will be designed specifically to detect and characterize Earth-like planets around Sun-like stars. Using advanced coronagraphs and star-shade technology, it will block out the overwhelming light of host stars, revealing faint planets and their atmospheric compositions. Scientists will be able to detect oxygen, methane, water vapor, and other potential biosignatures, mapping habitable zones with unprecedented precision. Parallel to these efforts, ground-based observatories will continue to push technological boundaries. The extremely large telescope in Chile, with its 100-foot primary mirror, will provide astronomers with the ability to analyze exoplanet atmospheres in unparalleled detail. Spectroscopy from these instruments will allow us to detect chemical disequilibria indicative of biological activity. Combined with the power of AI-driven data analysis, these observations will identify patterns invisible to human eyes, unlocking insights into life that may operate on different biochemistries than our own.
Robotic exploration and sample return missions will also play a crucial role. While telescopes allow remote observation, future spacecraft may be capable of traveling to nearby habitable worlds or their moons to collect atmospheric or surface samples. Such missions will require advances in propulsion, navigation, and life detection instruments. Solar sails, ion propulsion, and next-generation nuclear engines could reduce interstellar travel times from centuries to decades, making direct investigation of exoplanets a feasible reality within this century. Beyond physical exploration, the integration of artificial intelligence and machine learning is revolutionizing the study of life in space. AI systems can analyze massive datasets, simulate planetary environments, and model potential biospheres. These tools enable scientists to predict where life is most likely to emerge and to optimize observational strategies. Machine learning can also identify anomalies that may indicate unusual chemical or biological processes, guiding missions toward the most promising targets. As humanity steps into this new era, international collaboration becomes essential. Space agencies, universities, and private enterprises must work together to share knowledge, technology, and discoveries. The challenges of exploring and studying life on distant worlds are too vast for any single nation or organization to tackle alone. By fostering global cooperation, humanity can ensure that exploration is conducted ethically, sustainably, and efficiently, with a shared goal of understanding the universe and our place within it. The discovery of K2-18b also catalyzes advancements in planetary protection and bioethics. Establishing protocols for avoiding contamination, both of alien biospheres and Earth, will be critical. This includes quarantine measures, sterilization techniques, and remote observational strategies to minimize human impact. Humanity must balance its curiosity with responsibility, ensuring that the act of discovery does not inadvertently destroy the very life we seek to understand. The next frontier is the study of planetary ecosystems over time. Observatories capable of long-term monitoring will track changes in atmospheres, weather patterns, and seasonal cycles. This will reveal the dynamics of alien climates and the interaction between life and environment. Scientists may even observe phenomena analogous to Earth's seasonal carbon cycles, photosynthesis, or microbial population shifts, providing insight into the universality of life processes. Another exciting avenue is the search for technological civilizations. With billions of potentially habitable planets in the galaxy, it is statistically likely that some may host intelligent life. Advanced telescopes could detect artificial lighting, industrial pollutants, or megastructures around distant stars. Combined with radio and optical SETI initiatives, humanity could not only confirm life, but witness the emergence of civilizations beyond our own. Such discoveries would redefine our understanding of technology, society, and our place in the cosmos. The implications for humanity's long-term survival and evolution are profound. Knowledge of other life-bearing worlds may inspire technological innovations, resource-sharing strategies, and planetary management techniques. Learning from distant biospheres could help us understand sustainability, ecological balance, and resilience, lessons crucial for preserving life on Earth. By observing how life thrives under diverse conditions, we gain a mirror to reflect on our own stewardship of the planet. Finally, the discovery of K2-18b underscores a deeper truth. The universe is alive, adaptive, and abundant. Life is not rare, it emerges wherever conditions allow, transforming worlds and weaving an interstellar web of biology. Humanity's role is no longer passive. We are not mere observers, but participants, explorers, and custodians. The next decades will see unprecedented missions, technologies, and discoveries that will expand the scope of human knowledge, connecting us to a galaxy rich with life. As we prepare for this future, it is clear that the journey has only just begun. The discoveries of today, K2-18b,
Its biosignatures and the potential for countless other living worlds are the foundation upon which humanity will build a cosmic legacy, exploring, protecting, and understanding life beyond Earth. The universe has revealed a secret long held in the darkness of space. Life is everywhere, and humanity is now equipped to witness, learn from, and join this vast interconnected web.
The discovery of K218b is not just a milestone in astronomy, it is a turning point in human history. For centuries, humanity has gazed at the stars, wondering if life existed beyond our pale blue dot. Now, with the James Webb Space Telescope revealing a planet 120 light-years away, teeming with biosignatures, that question is no longer theoretical. Life, it seems, is not a rarity, but a cosmic inevitability. K218b challenges every assumption we have held about the universe and our place in it. It teaches us that life is adaptable, resilient, and pervasive. From the swirling debris rings around distant stars to the chemical whispers in alien atmospheres, the cosmos is alive with activity, experimentation, and evolution. This realization should reshape not only science but philosophy, culture, and the very way we view ourselves. Humanity is no longer an isolated species on a small planet. We are members of a galactic community of living worlds. The implications for science are profound. We are entering an era where the study of life is no longer confined to Earth. By observing alien biospheres, we gain new perspectives on evolution, climate resilience, and planetary ecosystems. We can compare how life thrives under extreme temperatures, chemical compositions, and atmospheric pressures. Each discovery adds a page to the universal story of biology, showing us patterns, connections, and principles that transcend our own planet. Equally important is the ethical responsibility that comes with this knowledge. As we explore these living worlds, we must do so with respect and care. K218b reminds us that life is not unique to Earth, and with that comes the duty to preserve, protect, and study it without interference. Future explorers and scientists must balance curiosity with stewardship, ensuring that discovery does not destroy what it seeks to understand. But perhaps the most profound lesson K218b offers is about human potential. Just as we have developed the technology to detect life 120 light-years away, so too can we apply our ingenuity, cooperation, and innovation to challenges here on Earth. Understanding life elsewhere encourages us to better manage our own planet, protect biodiversity, and embrace sustainable technologies. In studying distant worlds, we are also learning how to safeguard our own. Now is the time for action. We must continue to invest in science, technology, and exploration. The next generation of telescopes, observatories, and interstellar missions will expand our reach, allowing us to study hundreds, if not thousands, of potentially habitable planets. AI and machine learning will enable us to analyze vast cosmic datasets, detect subtle biosignatures, and unlock the secrets of alien life. Every new discovery will bring humanity closer to understanding the full scope of life in the universe. Equally vital is public engagement. Discoveries like K218b are not just for scientists, they belong to all of humanity. Education, media, and outreach programs must ensure that people worldwide understand the significance of these findings. Humanity's journey into the cosmos is a shared story, a narrative that binds us together across borders, cultures, and generations. By fostering curiosity and appreciation for the universe, we inspire future explorers, scientists, and thinkers who will continue this quest. The moment we definitively confirm that life exists beyond Earth will be transformative. Societies, philosophies, and cultures will inevitably evolve in response to this knowledge. We will gain a new sense of perspective, realizing that our actions on Earth and eventually beyond have consequences not only for ourselves, but for the broader cosmic ecosystem. Humanity will learn that we are both students and caretakers of life, tasked with understanding and preserving its diversity. So what should we do next? Support space exploration, advocate for science education, and embrace the unknown with curiosity and humility. Follow the discoveries of telescopes like James Webb, Hubble, and the future Habitable Worlds Observatory. Celebrate each biosignature, each planet discovered, as a step closer to understanding the universe and our role within it. And remember, K218b is only the beginning. Thousands of other worlds await, each with its own story, its own chemistry, and, perhaps, its own life. As we gaze at the stars tonight, we can do so with hope, excitement, and responsibility. Humanity is no longer alone in imagination. Soon, we will no longer be alone in reality. The universe is alive, teeming with possibilities, and K218b has opened the door to a new era. Our journey has just begun, and the cosmos awaits with secrets ready to be uncovered. The discoveries made by James Webb and those yet to come remind us of a simple truth.
Life is everywhere, and humanity has the privilege and duty to witness it, learn from it, and protect it. We stand on the threshold of a golden age of exploration, a time when the boundaries of science, philosophy, and human understanding will expand beyond anything we have imagined. K218b is not just a planet. It is a mirror reflecting what humanity can achieve, what it can learn, and the responsibility it now carries as a member of a living universe. The universe is calling, and humanity must answer. Explore, discover, protect, and marvel at the cosmic tapestry that surrounds us. Life exists beyond Earth. The journey to understand it is ours, and the possibilities are limitless.